Early warning signs. Early warning signs. The alertness in determining early warning signs in well control is of the utmost importance to wellbore safety. Careful observance and positive reaction to these signs will keep the well under control and prevent the occurrence of a well flow situation. The various signs that have been recorded as early warning indicators are not consistent in all situations. The signs, however, may have to be used collectively, as one indicator may not accurately provide the warning of getting into an unbalanced situation. Even though the series of signs may change between wells, early warning indications can be found from the following list. Increase in drilling rate of penetration. Increase torque and drag. Decrease in shale density. Mud property changes. Increase in cutting size and shape. Increase in trip, connection, and slash or background gas. Increase in the temperature of the return drilling mud. Decrease in D exponent. Increase in drilling rate of penetration, drilling break. When drilling ahead and using consistent drilling parameters, as the bit wears, a normal trend of decreased penetration rate should occur. If the differential pressure between the hydrostatic pressure of the drilling fluid and formation pore pressure decreases, an increase in the drilling rate occurs as the chip hold down effect is reduced. A general and consistent increase in penetration rate is often a fairly good indicator that a transition zone may have been penetrated. A rapid increase in penetration rate may indicate that an abnormal pressure formation has been entered and an underbalanced situation has occurred. Increased torque and drag. Increased drag and rotary torque are often noted when drilling into overpressured shale formations due to the inability of the underbalanced mud density to hold back physical encroachment of the formation into the wellbore. Drag and rotating torque are both indirect and qualitative indicators of overpressure. They are also indicators of hole instability and other mechanical problems. Torque and drag trend increases often indicate to the driller that a transition zone is being drilled. Up drag and down drag as well as average torque figures should be recorded on each connection. These trends are valuable when comparing other trend changes. Decrease in shale density. The density of shale normally increases with depth, but decreases as abnormal pressure zones are drilled. The density of the cuttings can be determined at surface and plotted against depth. A normal trend line will be established and deviations can indicate changes in pore pressure. Increase in cutting size and shape. In transition zones or in abnormally pressured shales, sandy shales and bedding sand streaks, the shales break off and fall into hole because of underbalanced condition, pore pressure greater than mud hydrostatic pressure. Water wetting may further aggravate this problem. Changes in the shape of shale cuttings can occur as an underbalanced situation is developing. The particles are often larger and may be sharp and angular in the transition zone. Extra fill on bottom may coincide with the trend change. Severe sloughing will often cause changes in pressure and stroke relationship. Normally pressured shales produce small cuttings with rounded edges and are generally flat, while cuttings from an overpressured shale are often long and splintery with angular edges. As reduction of hydrostatic differential between the pore pressure and bottom hole pressure occurs, the hole cuttings will have a greater tendency to come off bottom. This can also lead to shale expansion causing cracking, and sloughing of the shales into the wellbore. Changes in cuttings shape and cuttings load over the shakers needs to be monitored at surface. Mud property changes. Water-cut mud or a chloride, and sometimes calcium, increase that has been circulated from bottom always indicates that formation fluid has entered the wellbore. It could be created by swabbing or it could indicate a well flow is underway. Small chloride or calcium increases could be indicative of tight, non-permeable, zones that have high pressure. In certain type muds, the viscosity will increase when salt water enters the wellbore and mixed with the mud. This is called flocculation because the little molecules of mud solids, which are normally dispersed, form little groups called flocks. These flocks cause viscosity and gel increases. In other type muds you might see a viscosity decrease caused by water cutting, weight decrease. This is true when operating with low pH salt-saturated water-based muds. In oil muds, any water contamination would act as a solid and cause viscosity increases. Gas-cut mud would be fluffy and would have higher viscosities, and lower mud weight. It is essential to know that trend changes are more important than actual value of the change. Increase in trip, connection, and a background gas. Return mud must be monitored for contamination with formation fluids. This is done by constantly recording the flowline mud density and accurately monitoring gas levels in the returned mud. Gas-cut mud does not in itself indicate that the well is flowing, gas may be entrained in the cuttings. It must be treated as early warning of a possible kick. Therefore pit levels should be closely monitored if significant levels of gas are detected in the mud. An essential part of interpreting the level of gas in the mud is the understanding of the conditions in which the gas entered the mud in the first place. Gas can enter the mud for one or more of the following reasons. Drilling a formation that contains gas even with a suitable overbalance. Temporary reduction in hydrostatic pressure caused by swabbing as pipe is moved in the hole. Pore pressure in a formation being greater than the hydrostatic pressure of the mud column. Change in the temperature of the return drilling mud. The temperature will normally take a sharp increase in transition zones. The circulating rate, elapsed time since tripping and mud volume will influence flowline temperature trends. The temperature gradient in abnormally pressured formations is generally higher than normal. The temperature gradient decreases before penetrating the interface and, therefore marked differences can give an early indication of abnormal pressures. This is usually a surface measurement which has a tendency to be influenced by operating factors. Decrease in D exponent. The D exponent will be plotted by the well loggers and maintained current at all times. This value was introduced in the mid-60s to calculate a normalized penetration rate in relation to certain drilling parameters. The D exponent may be corrected and normalized for mud weight changes and /or ECD, equivalent circulating density, by the following. A plot of DC exponent versus depth in shale sections has been used with moderate success in predicting abnormal pressure. Trends of DC exponent normally increase with depth, but in transition zones, its value decreases to lower than expected values. Mud logging companies have further variations/models which try to normalize for other parameters, such as bit wear and rock strength, to varying degrees of success. Positive kick signs. A kick occurs when the hydrostatic pressure of the mud column in the well is less than the formation pressure provided that the formation has the ability to produce. A kick is a positive indicator that formation fluid is entering the wellbore and secondary well control must be initiated. Recognizing a kick while drilling. Flow into the wellbore causes two changes to occur in the mud circulating system. Increase of active mud system volume. The mud return flow rate exceeds the mud flow rate into the well. Drillers should make sure crew hands notify them if they do anything to change the level in the pits. If crew hands are adding volume to the pits, they should also notify the driller when they stop adding volume. Recognizing a kick while tripping. Flow into the wellbore will cause improper hole fill up. If this is seen, a flow check should be performed. If the flow check is positive, then the well should be shut in. If the flow check is negative, the drill string should be run back to bottom to circulate bottoms up. Stripping may have to be used here. When tripping in the hole, the trip tank should be used to ensure the correct mud displacement is taking place. On trips, the drill crew should be able to recognize a 5-barrel kick or less. During drilling, the crews are generally able to recognize a 10-barrel kick or less. The size or severity of a kick depends on the volume of foreign fluid allowed to enter the wellbore, which depends on the degree of underbalance, the formation permeability, and the length of time it takes the drilling crew to detect that the well is kicking. Kick behavior. A comparison between oil and water-based muds. Due to high temperatures and pressure, a small gas kick can turn into a serious well control problem with oil-based muds. Solution gas can become dissolved and miscible. The reason for this is that the gas remains in solution until it reaches its bubble point. In the same way that gas in disposable lighter remains in its liquid phase until the pressure is relieved.